Today we have the pleasure of hearing from Dr. KiranKumar Kurvinashhetti, who is a MyTax postdoctoral fellow in Dr. Amin Kameli's lab in the Department of Biomedical Engineering. Dr. Kurvinashhetti has received his Bachelor of Engineering in Electrical and Electronics Engineering from Basaveshwar Engineering College in India, followed by a master's in Power Electronics from the National Institute of Technology, also from India. He then pursued a PhD in Bio, Micro, and Nanosystems at Concordia University in Montreal, Canada. His PhD research focused on generating electricity from algae to power low-power electronic devices. Additionally, he has collaborated with the University of Montreal on electrocatalysis for clean energy applications. Currently, here at the University of Calgary, he is developing wearable biosensors by integrating bio-nanoelectronics and electrochemical sensing technologies for continuous health monitoring. Particularly, he's assessing stress conditions using sweat as a biomarker. Outside the lab, he enjoys reading literature and playing cricket. And today, he will be sharing his presentation titled, "Your Sweat Tells Your Stress, Wearable Microfluid Sensor for Health Monitoring Applications."
Hi, good afternoon to all. Your sweat tells your stress, a wearable microfluidic sensor for health monitoring applications. I have taken with me my chip, so whenever I'm presenting, you can pass it by and take a look at it. So I'll just give it here at the beginning. Maybe after some time you'll understand what it is. So this work is done in collaboration with Biomims and Bio-Inspired Microfluidic Laboratory, and I had lab of Dr. Amin. These are the colleagues who work with me in this work. I'll start the talk with introduction about wearable technology and sweat as a diagnostic biofluid, microfluidics for sweat collection and off-body analysis, fabrication of the chip that I just gave it to you on body for near real-time sensing, and mechanical testing of the chip, human subject testing and the results, conclusions, and the future perspectives. The first generation wearable devices, which all of us have now, like smartwatches, wearables, and as well as the smart rings, these provide some vital health information such as heart rate, ECG, sleep health, and all the vital informations. And in 2025, beyond the step counting, the wearable tech also promises some medical grade data at the Consumer Electronics Conference Society in 2025. However, the first generation devices use only the vital information. To measure the biomolecules, we're still depending on the lab techniques. We have to go to the labs, provide our blood samples, and get the testing done in order to understand the biomolecules present in the body, right? So, what are the current challenges of going to the lab and performing the test? So this is, first of all, it's invasive. It requires blood samples with the needles, and it's a time consuming. If you have to test it, you're not testing in the real time. You're giving the sample today and getting the results maybe next day or 2 days or 3 days after that. And also it's non-real time and non-continuous. You're not able to understand every few minutes what's going on with the biomolecules. So to overcome these challenges of the first generation and the laboratory techniques, there are new generation coming up, wearable biosensors for a second generation, which can measure the biomolecules present inside your any body nucleus. Majorly focused on interstitial fluid, saliva, tears, and sweat, which are easily available. So one classic example that I would like to give you is the continuous glucose monitoring, which many people are commercially using right now, which they can wear on the body and measure continuously every few minutes or every minute of their glucose data for 14 days. And this one uses the interstitial fluid. Interstitial fluid is a fluid in between the blood and the skin layers. So it's a kind of a middle layer in between that, and techniques have been advanced in order to sense the glucose from interstitial fluid. Now, and this is a minimally invasive technology because still it has to go through the skin and puncture, right? So what if we have to do completely non-invasive technology? There should not be needles, there should not be minimally invasive, completely non-invasive. Then the answer for that is sweat. Can we diagnose or can we understand our health using sweat? The answer to that is yes. We can understand our health using sweat. Sweat. Increase in the body temperature. Whenever there's increase in the body temperature, what happens is brain sends neurotransmitters to the sweat glands, and with the sweat glands, the sweat produces and comes on the surface of the skin, right? The epidermis, like that. This sweat is consisting of a composition of sweat it has the metabolites such as the lactate, glucose, urea, uric acid, creatine molecules, and as well as hormones such as cortisol, proteins, electrolytes, nutrients, alcohols, and drugs as well. And the recent advances in the clinical applications have found that more than 26,000 biomarkers are present in sweat. So which is quite a new advances are going on in the sweat. And the clinical applications have found that the tuberculosis specific biomarkers are present only in sweat, not in blood. And cancer specific biomarkers, Parkinson specific biomarkers are present in sweat. And cystic fibrosis is a condition where there's a problem with the lung in the newborn babies, where the gold standard is sweat chloride concentration. It's not the blood testing. It's only the sweat chloride concentration measurement gives us the idea of diagnosis of the cystic fibrosis. So we understood that a lot of biomarkers are present in sweat, which we can use for diagnosis and prognosis applications, right? So in order to realize the sweat-based wearable technology, what should its components look like? So first, we need to extract the sweat, right? We need to have a sweat on the skin surface. It's by either a natural process where you do exercise or in a sauna or a heat environment, or there's another technique where you can generate sweat in a rest condition. So that is by iontophoresis, which is called as where you apply a small electrical current onto your skin to generate a small amount of sweat samples to do the analysis. So even you can not only do the exercise, you can also generate sweat in your rest conditions that it can be used as a continuous sensing. And once the sweat is generated, we need to collect the sweat. And to collect the sweat, microfluidics is a key part. And I'm going to explain what it is and how we fabricate things in the next slides. Next, once the sweat is collected, we need to do a sensing. For example, we are focusing on cortisol, glucose, or any other molecule that you're interested in it. We need to sense that molecule. So there's another component of biosensing involved in it. Next is we need to do a power source. We need to give a power to read and understand the data, right? So it's electronic readers and the power source is required. Next, once we generate enough data for continuous sensing, from the continuous sensing, for example, every minute or 2 minutes, then we can use a lot of data to do a predictive machine learning to predict the health applications. So sweat, especially focused on a sweat, it could have applications in fitness tracking, hydration monitoring, and for elderly people in diagnosis and prognosis, where it's a completely non-invasive technology, and also could be used as a personalized medicine. So only particular subjects, we can get a lot of data and understand what is the baseline for them. It's not a generalized medicine. You can go for a personalized medicine as well. And also it could be used, these data, to do a preventive healthcare understanding. So I explained about microfluidics is for a sweat collection. So what is microfluidics? It could be a new term for many people. So microfluidics is a key for a wearable biosensor. So what it is micro, which is 10⁻⁶ in micro scale, either the sample value or the dimensions of the chip. Any one of them, if it's in the micro scale, we call that as a microfluidics. So let's say one example of that is a microfluidics for a blood analysis. So here you could see a small fingerprint. We can collect the blood samples, and if passed with this small chip, these dimensions are in micron scale, and the samples are also in, let's say, 100 microliters or 1,000 microliters. And we could use this analysis for healthcare applications. Similarly, there's another example where you could see a plasma is separated out of the blood from the small microfluidic chip. You could see here the plasma will be separated. And you can collect the plasma to do the analysis. So this is a concept of microfluidics where it's used in the healthcare applications. So the best advantages of these are it's First of all, we can have a decreased reagent consumption. The consumption of the samples are pretty less, and a small economic footprint. These can be done in less than $1 or a cents, and easily can be automated and integrated into electronics and other systems that we can treat it as a commercial device. We can use it as a commercial device. So now we understood microfluidics, the sweat, and everything. Now, can we measure sweat? Can we measure stress through sweat? Is it possible? Yes, there are a lot of stress biomarkers, right? Especially the stress biomarkers are cortisol, dopamine, epinephrine, and serotonin. So all these are cortisol, and all these are the stress biomarkers. Many more could be understood and can be discovered using the sweat collection analysis. So right now, these are the major ones. And amongst this, cortisol in sweat is present at a higher concentration than in these three. Therefore, we focused right now on cortisol to measure concentration of cortisol in the sweat samples. So what happens, how the stress and cortisol are related, right? So whenever we threaten, whenever we feel threatened, what happens is our brain or a nervous system sends signals to the adrenal glands. It produces the cortisol and adrenaline. These cortisols and adrenaline pass through the bloodstream. So these bloodstream, what happens is whenever through the diffusion process, the cortisol from the blood enters into the sweat samples. When it happens, when the body responds to this emergency situation, when we threat, what happens to the body conditions are there will be increased blood pressure, increased sweating, fast breathing, accelerated heart rate, and digestive slowdown. So many factors affects to the health when there is a stress happening. And that's because of the release of cortisol into the bloodstream. So now, how can we develop some microfluidics to collect the sweat and do the analysis of cortisol in it, right? So here, one of our colleagues, Shajari, has worked on this development of microfluidic chip, which can collect the sweat samples in these fibers and do off-body analysis. We could take it to the lab and then do the analysis. What happens is, here, these are the several inlets. From this, the sweat is collected and flows through this microfluidic channel and stores in these fibers. So what they have done is they applied this microfluidic chip to different body locations, such as the forehead, armpit, lower back, and hand. So let me show you a video of how it works. Let's say whenever subject is under exercise condition where it generates a sweat, you could see here. So you can see here where the sweat is collected into the fibers. Sweat is collected into these fibers when this exercise is done. Later on, once this sweat is collected, we store them, the chip, in a minus 80 degrees Celsius in the freezer. And later on, we only take the fiber cut and then centrifuge them for 10 minutes at 11,000 RPM. Further, when we collect the samples, we do enzyme-linked immunosorbent assay, which is by immunosensor assay, where we understand what is the cortisol concentration in the sweat samples. And this approximately takes 2 hours of time because it's a pretty long process to involve in it. So when they have done different body parts, let's say they attach to an armpit, back, forehead, and hand, they found that the different cortisol concentrations are present in different body locations. It is because each body part has a different sweat glands. So with respect to that, the cortisol concentration slightly varies. And it found that with the armpit, the cortisol is around 100 to 125 nanogram per ml in sweat samples. So once the cortisol is understood, it's correlated with the stress condition. So usually right now, how stress is measured is a psychological test where you go through a perceived stress scale test where you will be asked some questions on are you feeling stressed, some psychological questions. Then based on that, you understand what is your stress levels. Is it stress scores? Based on that, you will assign the stress scores. So 0 to 13 is considered as a low stress. 13 to 26 is a medium stress. And 26 to 39 is considered as a high stress. So once before doing the exercise and taking the the sweat samples, subjects are asked to go through these questions. They answer these questions, and once we measure, after the sweat sample is collected, we measure the cortisol levels in the samples. Then let's say cortisol concentrations are low, it's from 1 to 5 nanogram per ml, medium is 5 to 25 nanogram per ml, and high is 25 to 125 nanogram per ml. And these are correlated with perceived stress tests for different body locations. Then we found that armpit sweat cortisol concentrations are closely in correlation with the psychological answers. So it's found based on that is concluded that armpit is a good location to get the sweat samples to do cortisol analysis, which is a stress analysis. Similarly, we did work on horse sweat samples as well. Still the work is underway. You could see we attached these sweat samples and we did kind of exercise method, ask the horse to run for some time, and then we collect the sweat samples into these fibers and do a conventional analysis. You take this chip out and then cut the fibers, do a centrifuge, collect the sweat samples, and do ELISA technique or the conventional technique. Until now, we understood we can collect the sweat samples in microfluidics in fibers and do the analysis because it takes only 1 to 2 microliter of samples, pretty small value, and it can be easily collected in the microfluidics chips. But now, can we do on-body real-time cortisol measurement? This was off-body now. Again, we need to depend on the lab to do the analysis. But can we do all of this on the body itself and a near real-time understanding of cortisol? Just to do this, the objectives of the work were to design wearable microfluidics to measure a real-time cortisol in the sweat and validate the developed cortisol sensor with the ELISA. Let's say earlier we did ELISA separately. Now, can I combine that ELISA technique same time and at the same time the biosensing at one chip? Is it possible or not? That was the objective. And the sub-objectives were the goal was to do a one-time cortisol measurement, not a continuous at the moment, to do a one-time cortisol understanding and a near real time. I'll explain why I call it as a near real time in the next slides. And a quick and fast measurements, not as 2 hours to take that, which that takes in the ELISA. And most important is user comfort. That has to be pretty day-to-day activities. Still, they have to be comfortable reading it and getting the data. So to do all these objectives, there's still a lot of challenges exist in the wearable biosensors, right? So first major important is efficient sweat sampling and manipulation of the sweat sampling. It's not easy to collect the sweat. So you can generate the sweat, but not easy to collect the sweat and do it on body real-time analysis. And also the accurate measurement of biomarkers is tricky. The sweat consisting of 26,000 biomarkers, as I explained, a lot of biomarkers in it. If you have to specifically sense any one particular molecule, it's a challenging. It's not easy. So the community is working on in order to do specific sensing and a need for continuous sensing for a prolonged period that we can use it for personal applications or preventive medicines. To do this is the device where we fabricated, which can do on-chip, on-body real-time sensing. So how the process works is we first select the materials. The materials are paper and polymer-based materials. The reason we are choosing the paper and polymer-based materials is because we want to have it a scalable technology that can be scaled and also a mass-producible fabrication. So we could also do, let's say, a 1 million or 10 million chips in just 1 hour or 2 hours, right? Because when we want to make it a commercial applications, it has to be more, it has to be a scalable application. It should not be only limited to a lab scale. And then we design the microfluidics in order to manipulate the sweat as required to do a real-time sensing. And for the prototyping at the moment, we used a laser cutter, which is a CO2 laser cutter. And then we assemble it, the assembly of the schematics is shown here. So to give a brief, it has a different layers. So this one is the main microfluidics layer, which has a pressure sensitive adhesive, which is a paper-based material. And other hydrophobic and hydrophilic are polymer-based materials, which guides the sweat in the directions that we want in order to sense the cortisol. Once I am assembled, it looks like this. So I just pass the chip, maybe you have it, you can look at it. So how it works, what is the goal of our chip is, first, the sweat has to collect in this inlet, and then it will pass through the main microfluidic channel. This is a main microfluidic channel, and this is a sensing area where cortisol is sensed. And these two are the redox chambers where electrochemical sensing takes place. I'll explain this stuff in the next couple of slides. And this is a vent which is required for the fluid to guide properly to the sensing area. And once this is, when the fluid reaches the sensing area and the redox chambers, then it goes to a side channel and stores the sweat in this side fiber. Similarly, it goes on the right side as well and stores the sweat in this right fiber. So you can see the operation of the chip right now here. So first it fills the inlet, comes to the electrode, and then redox, then goes to the side fibers. So once the side fiber is filled, then it goes to the left side, right side fiber fills. So it is important to have a sequential filling in order to do the analysis for us. For example, first the inlet has to fill, then it has to come to the sensing area, which is this part. Then followed by that, it has to go to a redox chambers because we have a redox molecules here. And side fiber 1 and side fiber 2 then it goes side fiber 1, side fiber 2. Side fiber 1 and side fiber 2 are to collect the sweat samples, as I explained in the previous microfluidic chip, where we can store the fluid at the same time and sense and validate both our technology and conventional technology. We can validate both at the same time or near real-time applications. So here, if you see a plot where we did analysis of the filling time, inlet, sensing area, and the redox chamber, all these three and we did for different body fluids, artificial sweat, which we actually prepare, and saliva samples, plasma, and blood. So for all these bloods, plasma, and saliva, we could see the reaching the filling time from inlet to redox chamber is pretty less, 50 seconds, and very close by. This is important for us, whereas the side fiber 1 and side fiber 2, as I explained, the side fiber 1 and side fiber 2 are to store the samples. They're not helping any sensing applications, but they're storing purpose. So it will not affect much for the sensing, even though you use a different body fluids. So it could be, we can use it as a point of care analysis. It's kind of a term where you take your samples and add into it, you get your data. So that's not a variable, but a point of care analysis applications. The chip with a slight modification can be used as both applications. And one more thing is, as the viscosity increases, the time to take to fill the chamber increases because of the viscosity. Next, when we did the off-body analysis, then we also did the on-body analysis. We could see we attached it to a human subject, and we asked them to do exercise. I will go through a learning protocol at the end of the after a few slides, where here you see it's a pretty long video, 13 minutes. I'll just show it to you. Here you can observe it's following the same sequence as I mentioned. It is important for us to have the same sequence in order to do the sensing. So if you observe here also the inlet, sensing area, and the redox chamber, it takes less than 3 minutes, whereas the side fiber filling 1 and side fiber filling 2 takes 13 minutes of time. And that actually depends on each individual because of its sweat rate condition, sweat rate generation, right? The sweat rate, what happens is it depends on each individual because it depends on environmental factors, where in which room he is in, or what is his age, clothing, ambient temperatures, etc. And the pathophysiological conditions like the genes, hormones, and neurological medicines. You're taking some medicines that may increase the sweat rate or that may give you more sweat as well. So it all depends on different factors. So once we've done the on-body analysis, now we cannot do for hundreds and thousands of subjects on body chip. It's quite difficult, right? So in order to do that, what we did is we mimic the different sweat rate generation by creating a different flow rate using a syringe pump. Syringe pump is a pump where you create a flow rate depending on your requirements, like 10 microliter per minute or 20 microliter per minute at a low moderate exercise, higher moderate exercise. You can vary the sweat rate by varying the flow rate of the pump. right? So for example, here you see this condition also. The filling sequence is same, which indicates even if there is a different flow rates, the filling sequence doesn't affect, which means the functionality of the chip will not affect. And we'll go through the side fiber without this channel. That's what we did for 10 microliter per minute, 20 microliter per minute, and 40 microliter per minute. And we will see for each of, even though what happens is on a smaller flow rate, it takes more time for the fluid to fill up. Whereas for a moderate or a higher flow rate, which is 20 microliter per minute and a 40 microliter per minute, again, the filling time takes pretty less time, within less than 50 seconds. In side fiber 1, side fiber 2 takes slightly higher because it's not stores the applications, it doesn't have any impact on the sensing applications. Now we discussed all the physical characteristics of filling time analysis. Now I'll come to a redox diffusion. So I explained what is redox, right? Here there are 2 redox chambers. These chambers are important because once the sweat comes in contact with these chambers, there will be a diffusion of these redox molecules on the surface of the sensing area. I'll show you a video. This is a very fast forwarded video, it's not the exact same time, just give you some analogy of how it works. Once that is added, it's quite difficult to see it here, but what happens is when the sweat enters these channels, diffusion starts happening on the surface of the electrode. See, this is the area point where we did the analysis, where all the video is recorded and did a video analysis to understand the concentration of this redox on the surface of the electrode. You see here, this is the experimental work with the video analysis. And also we did a simulation of this study where you use the constant multiphysics to simulate the diffusion process of the sensing area. And as I explained, the side fibers are only for collecting the sweat samples. They are not having any applications in sensing. So we tried what happens if we take off the side fibers. Does it use the same functionality or it alters the functionality? So it found that for all 3, the diffusion process is uniform. And after 10 minutes, we reach almost 45 millimolar and stabilize. So after this, we can read the data, cortisol data, clearly. And from 10 minutes to 20 minutes, ideally, we can read the data at any time. That indicates that the diffusion is uniform on the surface and should be able to read after 10 minutes. Now, that's it. When we have this on the body, right, when we're reading it on the body, what happens is the body, the chip might go through repeated cycles of bending, twisting, and all these on-body movements, right? It may not be straight as I shown in the video. So to understand these things, what we did was, does it affect the sensor performance? Does it affect the filling time analysis? To test that, we did a uniaxial tension cycle where we did a cyclic bending test. And we bend the cycles, we bend the chip based on the tension, on the uniaxial tension machine. And the stress strain curves are obtained. What happens is when the chip is bent by 40%, the induced stress rose to 0.4 megapascal here. But when it returned to a baseline, what happens is it gives a consistent hysteresis loop over 50 cycles. You see, this is a 50 cycle hysteresis loop. It starts from here, and then come back to the same place. So even after 15 cycles of cyclic bending test, it doesn't affect the sensor functionality. Because what happens is if there's any change in the hysteresis loop, then it indicates there's a structural damage in the chip. So even after 50 cycles, if you use it for a day or 2 with a lot of bending and things, it will not affect the sensor functionality. Then we also understood the filling time analysis of the chip after the bending cycles. So we did we understand the filling time of the chip. Well, up to 40 cycles, you can see here, the filling time is not affected much. It's as close to the without bendings. Whereas at the 50 cycles, this one is the 50 cycle, a slightly disruption of the chip has been found, and the filling time takes slightly more time. It can be attributed to the fact that the more bending, especially the cyclic bending, might have created the microfluidic channel slightly a curve or a bend. That may take more time for it to fill up. However, it may take a little bit more time to do that, but functionality of the sensing will not affect. So I'll come to the electrochemical sensing of cortisol now. So, see this one, as I explained, this is the inlet where the sweat samples goes in, and this is the sensor area, right? Electrode area. So what happens is in the electrode area, we deposit antibodies, and since the sweat samples which consisting of the several molecules, let's say the circle is a cortisol, this is a estradiol or a glucose, any other molecules. It has, as I explained, it has more than 26,000 biomarkers. I'm just taking a few as an examples. So once that comes, what happens is, and specifically the cortisol antigens bind to this cortisol antibody, because we need to sense specifically that particular signal, right? So once that is completely bind to the surface, then we read the electrical signal using electrochemical impedance spectroscopy. Its impedance varies based on the number of cortisol antigen and antibody interactions. And based on that charge transfer resistance, we understand what is the concentration of cortisol in the sweat samples. And I explained 10 minutes, and we gave it for diffusion also, if you remember the previous slide. The reason for that was to provide enough time for antigen of the cortisol and the antibody to bind it properly to read the data. So there's some incubation time required to bind the cortisols to the antibody. So that time we optimize for 10 minutes, and based on this, the diffusion of the chip is designed for 10 minutes. So here I have explained the cortisol, let's say different molecules, right? There's a blank electrode. Electrode, there's nothing on the surface of it. And cortisol, estradiol, glucose, and the lactic acid. Is it sensing specifically cortisol, or is it also interfering with some other molecules? To do this with the sensitivity, where RCT value, which is the EIS impedance value, we found that for cortisol slightly higher indicates that there's a strong binding of cortisol antigens to the antibody, which is only reading cortisol, not other specific molecules. So what is the redox, right? The redox concentration. What redox I said there is a redox concentration diffusion on the both sides. So what is the concentration of that we have added in the first? We use a dried redox. We deposit onto both the redox chambers. And first we tried the different concentrations. We tried at 2 millimolar up to 100 millimolar. And we found that at 50 millimolar, it's almost saturates. There's no impedance variation after that. So based on that, we choose 50 millimolar redox concentration. It means when we deposit on the redox chambers, 50 millimolar of redox on both the sides, 15 microliter of redox is dropped and allow it to air dry. So that's concentration is used for electrochemical sensing applications. Based on this, RCT values are explained the antigen-antibody interaction in the previous slide, which is here. Based on this antigen-antibody interaction, we did a calibration curve or artificial sweat. It means in artificial sweat, we synthesize, let's say, 2 nanogram per ml of cortisol, 10 nanogram per ml of cortisol, and understood their corresponding RCT values. Based on this RCT values and the concentration of cortisol, we did the calibration curve, and this sensor can read from 0, almost 1 nanogram per ml to 15 nanogram per ml. One advantage of this sensor is that this can read a minute variation in between 1 and 2 nanogram per ml. Most of the literature that others claim, they have a pretty wider range. They read from 1 nanogram per ml to 1000 nanogram per ml, where the sensitivity is not that high. Whereas in this case, we can also detect a minute changes in the cortisol concentrations. Now I'll come to a human subject test. The reason I call it a near real time is because it takes 10 minutes for incubation time. I'm not doing it exactly the same minute. That's the reason I'm calling it as a near real time cortisol measurement. To do the on-body human testing, what we did the protocol is first, we clean the body location. Let's say forehead, we're using it as a test body test. We clean the body location using alcohol wipes, and either we ask them to do a stationary biking or a treadmill, depending on their comfortness. If it's on the treadmill, we ask him to run 5 to 8 kilometers per hour at the moderate speed. And bike, moderate load intensity. The power for the bike, the power we use is 70 to 130 watts, which is almost 50% of the max power we use. And in both the cases for stationary biking and as well as the treadmill, we ask them to do it 20 to 30 minutes exercise depending on their sweat generation rate. Some people sweat in pretty lower time, let's say 5 minutes. Some people take 30 minutes, some people even 45 minutes to not sweat. So our whole idea is to get the sweat and go into the chip for sensing applications. So the time might slightly vary between each individuals, but it usually we observe from 20 to 30 minutes is a good time to get enough sweat into our chip. Then we need on-time, on-body, real-time cortical sensing. You see this one is the image where this microfluidic chip is on the body, and with a small cables, it's connected to a potentiostat, which is an electronic reader. Right now, what we use is a headband to keep this electronic reader invisible, and it's invisible inside this headband. And what happens is when the sweat comes in, it diffuses with this redox molecules, and after 10 minutes, directly you can see on the mobile application, what is the concentration of your cortisol. So in 6.40 nanogram per ml that we did one subject, we found 6.40 nanogram per ml as a cortisol values. Let's say this was the inlet before the sweat filling. This is the inlet after sweat filling, because till now I showed all the videos with a line, because to give you how the fluid flows. If I keep it with only sweat, it's not visible. It's clear fluid. It's quite difficult to observe that. But here I zoomed and just collected this one, how it works and looks like. Because when we do a real-time testing, we don't use dye. We use only the normal sweat, right? This is a sweat. This is a sensing chamber before and sensing chamber after diffusion on the body. You can see here, this is uniformly distributed and it's good to sense. And we did 12 subjects cortisol analysis from the different subjects, 12. And we found that the cortisol concentration varies from 0 to 15 nanogram per ml, depending on their stress condition, depending on their health and other things. And most of the subjects, the average was found to be a 7.5 nanogram per ml. It means it's a moderate stress or a low stress, I would say. And anything beyond, let's say, about 10 or 12 nanogram per ml is considered as a high stress conditions. Now, once I explain how we validate with the ELISA, right? We have a side fibers. As I explained, the side fibers, once the sweat samples once the exercise is done, all the sweat sample is collected in the side fibers. These side fibers are collected and stored in the minus 80 degrees Celsius, and again centrifuge for 10 minutes. And we do the ELISA, which takes 2 hours to validate the sensor performance. Once that is done, we correlated both ELISA output and our sensor, and both found a very correlation with ELISA as well as our wearable biosensor. And the R-square value was almost 0.90, which is very close relationship with our sensor development and the ELISA results. Now we also did it on different body locations. We did it for back, lower back, and forehead application. Forehead. What happens is we did 3 subjects, and a slightly different cortisol is observed for forehead and the back. It's not consistent performance, and we don't have enough data to do a statistical analysis at the moment, but we are working on to get more data to do which body location is better to get for stress, especially the cortisol concentrations. And next comes the morning, and especially cortisol varies and based on circadian rhythm. What happens is in the nighttime is pretty low. When you're sleeping, cortisol is low. And in the daytime, it's higher. Let's say from 8 a.m. to 4, 5 p.m., it's slightly decreasing with respect to day. And in the evening, it decreases, and night, again, it goes down, it's pretty lower values. That's a circadian rhythm. To test this, does our sensor also follow the sequence or not? We did 4 subjects for morning and evening, and on that, the mornings have a pretty higher cortisol concentrations, which is almost 10, 12, or 14 concentration, whereas the evening cortisol concentrations are slightly less in comparison to the daytime, which completely follows the circadian rhythm. Now, let me conclude what we have done till now. We developed the wearable microfluidics, which can do sensing or near real time of cortisol, and both on-chip sensing and validation of the ELISA can be done on the board chip. Earlier technologies that you do off-body analysis differently, and there's no validation. So this chip does both on-body analysis and as well as a validation of the with conventional techniques. And we did test the different body locations, lower back and upper head. Right now, a little bit of future works are we're working on more human subject tests to get more statistical data and analysis. And we can do more different health conditions, understanding acute and chronic stress, different disease involved pain, stress, and all these things. And role of diet on the stress, how the diet is affecting on the stress conditions, and more body locations, especially armpit, because it can be inside the body on your t-shirt or whatever. So it's not visible, and also you could use it as a regular commercial device, and you can understand your biomolecules from the sweat samples. So after we did a one-time cortisol sensing, now we're working on a continuous sensing, continuous cortisol. And this is the work is ongoing where the sensing technology is slightly different here. We used a molecular imprinted polymer. So how it works is here the same inlet sweat samples comes in, and this is a sensing area where we don't need any redox here because it's a different sensing method. And directly, as soon as the sweat enters the channel, it is for sensing. You could really in just 2 minutes start sensing the cortisol levels. And we have a capillary burst walls, which helps for us to manipulate the sweat samples. And then this flows into the microfluidic channel, goes into the fiber. Then from this fiber, slowly it enters to the other fiber. The whole idea is to sense cortisol every 2 minutes or every 3 minutes, and do it for a longer period of time to get a more data to understand is it varying, how it's varying for each individual. So for this, we let's say every 3 minutes, after 45 minutes, we are doing right now, and 15 cortisol data points we can collect in this 0 to 45 minutes of time. This is a microfluidic chip that explains the assembly of the chip. As I said, the final side fiber 2 takes up to 45 minutes to fill. And this is a continuous sweat flow, so there is no mixing of old sweat and the new sweat. That makes a difference. So you are continuously getting the new sweat and continuously getting the new cortisol data. You are not interfering with the old sweat. What would be the future prospect use of this technology, right? So let's say right now we did only cortisol. Later on, we could do multiple molecular analytes, right? We can sense glucose, cortisol, some inflammatory biomarkers, some other biomarkers which are important to do a continuous biopsy. Those things, and then devices like ours, which can be microfluidic devices. And we can generate a lot of data, like every 3 minutes, we can generate for a whole day. And this is a pretty good data to do. We can store them in the cloud and implement using the AI and machine learning models to predict the health there, especially the personalized health. We can understand using these technology. And also, these microfluidics can be used to do different biomarker applications, like we can understand different clinical side related biomarkers as well. So it's completely non-invasive technology and has a pretty bright future towards the personalized medicines and as well as AI-based sensing technologies.
Nice presentation, thank you. I'm wondering about the volume of the sweat in the chip. So do you measure, do you detect how much you get? Because you're getting at the end a concentration, so, and you're measuring the number of moles, let's say. So you need to know the exact volume in order to get the concentration. So do you measure the volume?
Yes, we required for the sensing around 5 to 10 microliter of the samples.
But if it's less than that.
It will not be less, because if it's not less, it will not fill the channel. So let's say if it is, if you see the filling time analysis, if it's not 10 microliter or less than that, it will not go into the electrode sensing it, it will not fill that. And also the side fibers, when you collect that, when we centrifuge them and get it, each side fibers can collect up to 20 microliters of sweat. And when we centrifuge, there will be some loss and all these things. So we can from each fiber, you can get approximately 10 to 12 microliter of samples. We have two of them. So 20 microliter is good enough to do the ELISA. And the commercial ELISA kits need only 2 microliter of samples. And that too, we dilute them. So if we really see that the sweat, we need only less than 1 microliter to do the analysis.
Okay, but the chamber needs to be filled in order for it to measure the amount of cortisol.
Yes.
So you know the volume of the chamber is constant, you use all the time to get the concentration.
Yes, you're right.
So you talked about how you want to use sweat to indicate stress. And you showed that the cortisol level varies during the day. And I'm just wondering, how much does it vary when people are stressed? Say, if you're yelling at somebody, how much does cortisol change? And then what's the temporal resolution of those changes?
Yeah. The cortisol changes, especially in the daytime, is, as I explained, is different from different body locations. Right now, for the armpit, is giving up to 125 nanogram per ml is a stress condition, or anything beyond 100 nanogram per ml is a stress condition. We did some analysis on the concussion patients as well. We also found up to 1000 nanogram per ml. Some patients have 1000 nanogram per ml, which is pretty high stress. And for concussion, measuring cortisol is important. In that case, the stress is too high for them. So the temporal resolution is, we have to understand that part, how, in what standard it's changing and how fast it's changing. We still need to understand that part, and still a lot of work is going on in that area. How much time it takes to change that.
Okay, but my understanding is that you're saying when people are stressed, the changes are much larger than, say, what you're seeing just as a baseline throughout the day. Is that right?
Yeah, it's right now still a question, because I would say we need, for every subject is different. Say for you particularly, if we observe your maybe healthy baseline is 10, for you stress could be 50. So we need to come up to that baseline and the personalized stuff. But for some people, the normal itself could be 80, and stress could be 100 or more than that. Right now, we are on the way towards the direction to understand all these questions. From starting is to understand real time, can we sense? Yes. The next is, if each individual, if we do one subject, different test, then we can understand what is their baseline, different type test conditions, stress condition, diet condition. Then we can come to a proper conclusion.
And as far as temporal resolution goes, is there a limit to how finely you can do your assays on the chip? Or is it basically you can make a sample as small as you want, and then I guess they're all in series with each other over time. And so I'm just wondering, can you do, by the second or less analysis?
Yeah, correct. The last one which I explained here, this one, this is a technique where you use a molecular imprinted polymer, which means the same sensor can be used for 1000 times. So you can read it for 1000 times. And the temporal resolution, what happens is, here you can sense every 3 minutes, because you need to have some incubation time for cortisol to come and sit on the surface of the electrode. There will be some settling time. There will be some time to require them to saturate. Then we can read it. Right now, in the literature and as well as we achieved up to 3 minutes with more research and more like a lesser samples and lesser smaller channels and highly efficient electrodes. We can even go for lesser than a minute. But right now, it's after 3 minutes we achieve. 3 minutes you can get a good 80% of the cortisol you can read. If we go higher, we can read 100%. So that's incubation time, decide a factor in size. Thanks.
Grant, stress can be caused by pain, emotional stress. maybe disease? Is it a way to identify the source of the stress, what causes stress?
Yeah, it's a good question. Right now, I don't have an answer for this. I need to read and come back to you. But it's tricky to say is it caused by emotional, physical, or any other factors. Diet or the sleep cycles. As I said, cortisol is pretty low at the night. If you're completely awake whole night, it might affect that too. So there are so many factors, physiological factors besides the cortisol variation. Still, we need to understand why specifically is it by psychological, diet, sleep, real stress. We have to understand those things. Yeah.
Yes, before I go to Adam, I have a question that goes off with the next question. When you do certain protocols, for example, if you're measuring people's sweat when they exercise on the bike or the treadmill, then you start measuring physiological stress rather than your emotional or psychological stress, right? So based on what you find in your future study, would this chip then come with like a suggestion on in terms of like, okay, if you want to measure your psychological, emotional stress, like you just wear it during the day and the sweat that's collected during the rest is what tells you that versus if you want to understand the physiological stress you're exercising?
Yes, you're right. So we are working on that chip as well, which is pretty smaller in dimensions and which can collect sweat for full day. And then each time it fills the chamber, it can read the data for you. And that human rest condition, let's say you're sitting, you're doing your work, and in the stress you're working and you get stress, all these things. In the rest condition also, we're working on that chip right now, still in the progress, and still work in progress, where we could understand the stress condition at rest and different activities as well. Yeah, this one especially for exercise based because we wanted to test the initial one. But right now, what we're working is can do at rest condition as well.
Yeah, great presentation. I'm just curious, and you might have mentioned this, if there is a relationship between cortisol levels and performance, whether that's like maximal strength or like endurance during, a fatiguing task. And could this kind of technology be used as like a training tool or a way to measure like recovery or something like that?
Yes, true. One of the great applications is the sports, right? Let's say the playing of basketball, but whatever the high intensity sports activities, where if you're measuring a real time cortisol, then you can understand the performance levels as well. The same thing that I showed the horse one. The horse sweat samples can be analyzed to do is this horse can do better in the race or not. So all these questions can be answered using real time measurements and by continuous collecting data, and then we can have a baseline, get all these answers.
Another question, then I'll go back.
Yes. If I'm not mistaken, you mentioned there are three sensory changes for the one time, yeah?
Yes.
How is the mechanism for nursing? Or how do you pressure sensor?
It's not it's there's no washing step required, even though there's small washing step required, it comes with the sweat itself. For some, let's say 100% cortisol molecules of sweat is coming up, that new sweat washes the sensor and is good for the next sensor. That's why we need 3 minutes of time to do this process. Completely taking off the sweat which is deposited and then coming the next sweat. That's how you give a little bit of time for incubation as well as washing that steps. We can do it for 15 times. But on the body, we can do 15 times. But off body, when we test it, we can go up to 1,000 cycles. We can do 1,000 times.
Venus? I'm thinking about the lifetime of cortisol and how it changes. And I'm wondering, I certainly appreciate the effort to have real-time or near real-time measurement.
Yeah.
But thinking about cortisol, why do you need real-time measurement for cortisol? It's a hormone, it's gonna stay in the body for some time. So it's not like it's producing up and down all the time. So, or maybe it is. So,
Yeah.
why the real-time in relation to cortisol?
Especially this one, when we were doing it, the application was for concussion patients. Let's say if the stress is really high, cortisol levels are high.
But it's gonna stay high for some time.
Yeah, this one helps to understand is it temporarily changing, what time it is changing. Right now, there's no technique to understand how fast it's changing. Just a theoretical understanding is yes, because whatever we do analysis right now, we do a blood samples. We do at some intervals of time. We don't know is it changing in 2 minutes when there is a condition, or is it changing in 1 hour, or it stays there for some time. So these kind of chips will help to understand those questions as well. Let's say, is it changing every minute? If it's really stressed, does it really go high and stay there for some time? And if we change the diet next day, does it come back? All these questions
Do
can.
you know the lifetime of cortisol? If it goes up, for how long it's gonna stay up? Like, is it gonna be degraded very quickly in the body, or it's gonna stay for hours?
I need to check that. I did not know yet. I need to check that one.
Other questions? While we wait for another question, I have one. So once you're done with all of the testing and let's say you're commercializing the sensor, do you think it would be useful to add like a temperature sensor in there?
Yeah, sure. The multiple sensing can be done. Right now, we just showed one. We have electrode where it can sense T4 at the same time, and temperature, pH of the sweat, and other parameters that gives us the health condition can be easily added. We did another one, another chip, I'm not showing here, which we can measure real-time pH with the sweat. Is it how it's changing with respect to time? Is it changing or not changing? If yes, what's changing? So it's possible to have multiple sensing modalities as well.
Does that change how big the sensor is or how usable it is, or does you incorporate all of that? Like all of the different molecules, for example, you said, would you be able to put everything in that little sensing area to
Yes.
have everything?
Yes, it's possible. So in this area, this is right now is a big one. Depending on the sensing technology as well and sample value will be required and the incubation time will be required. And also it comes with respect to that, it comes as the sensing electronics as well. Let's say you need to, you should not sense all at the same time, maybe wrong values. You need to sense or give a few milliseconds or seconds of time to do one by one. So this kind of a multiple reading also slightly tricky, but it is possible to do it, and work is going on that to do that as well.
Venus and then Amit.
So the amount of cortisol was different when you took the sweat from the back or from the.
Yes, yes.
Why do you think that's the case? Is it the sweat itself that is different between regions?
We found that sweat glands could be the reasons because each, let's say, the armpit has a higher sweat glands, which can produce higher sweat. And when there's a more sweat, the concentration of that could be through the diffusion process, there could be more molecules coming into the sweat glands. Still, that is a real correlation at the moment, but exactly why each sweat glands produce different concentration of cortisol, that we don't even understand why it is. But definitely, each sweat glands has different cortisol concentrations.
Wouldn't the more number of sweat glands not affected because you said it's the fixed amount of volume that goes into it? Then your concentration, even if you're getting more sweat glands in a location, the amount you're testing should still stay the same.
See, value is same. Value is not changing, but in that value, the concentration of cortisol could be higher and lower. Let's say I can take 1 liter of water and add some, whatever the content of it, right? Some could be smaller, I can add little or I can add more. So with respect to that, the value is same, but the cortisol in that value could be different.
The sweat cells, they are in the epidermis, and so
Yeah, on the
they,
skin side, yeah.
they produce the sweat right away towards the outside of the skin, or it diffuses into the interstitial fluid and then it goes out. So do you know exactly how they
It's a sweat glands, if you,
right away outside?
yeah. So here, this sweat gland, with the sweat gland, whenever there's a temperature difference, it comes to the epidermis of the sweat. Yeah, there's a gland where a neurotransmitter sends signals to that, and that sweat gland started producing sweat, and that directly comes from the surface of the skin.
Okay, Kiran, let's say you have a moment of stress, so cortisol is releasing your blood. If I take blood sample after 1 minute of that moment from the location of the body, I should be able to see increase concentration of the cortisol in the blood, right?
Yes.
What about the sweat? How long is going to take until they say increasing the cortisol?
Okay, it's excellent question. All right, let's say I'll give an example of a continuous glucose monitoring at the moment that we have in the commercial sector, right? People use it and it's based on interstitial fluid. So there is a time lag between blood and interstitial fluid. So similarly, there's a time lag between blood and the sweat. So what is the time lag? We need to do once we are doing the molecular improvement polymer, we're also working on collecting the blood samples and doing the analysis. So what is the lag? Let's say if you can read cortisol concentration from blood as 10 nanogram per ml at this 4 p.m. and then maybe at 4:15 p.m. you get the same in the sweat. Okay. We need to see what is that lag time period. Right now with the commercial glucose monitoring, it's around 5 to 6 minutes of lag, approximate. I don't know exact value, but approximate 5 to 6 minutes of lag because of interstitial fluid.
Because you mentioned you do monitoring every 3 minutes with the chip. If there's like 30 minutes lag between the cortisol release and it appears on the skin, then what's the purpose of the 3 minutes interval?
So let's say that's what the blood first we need to understand what is the lag period. If we can come up with that calibration curve, the blood, let's say it's 10 minutes or 5 minutes, then we can say, oh, it may be 2 minutes. We don't know at the moment. Then we can do that every 10 minutes required. So right now we do not know the answer yet. And with the sensing technology, we could able to achieve up to 3 minutes. Even though that is the case, the continuous glucose monitoring does every 30 seconds. It uses the every 30 seconds data. So, but still there is a lag of 5 minutes. So there's a lag. Definitely there's a lag between blood, interstitial fluid, sweat, and even saliva and tears. It's not the same time.
We had a question for Abel and then Osman and then Maui.
Great presentation. I don't know if you touched this in your presentation, but like, how do you see differences for competition with between genders? Female, maybe hormone, like a caution.
Yes, not done actually, but we can do. We are not done the male, female. We are working on test right now. So once we collect the data, we can definitely understand that part. But right now, we did not do it, but we are working on data collection at the moment. So we are taking care of these ones as well.
Do you expect any difference between them or like a hypothesis for that?
It could be. Could be. I do not know the exact answer at the moment. It could be.
Okay, Osman?
My question is an application question. Has anyone ever used this kind of sensing on elderly people when they walk? So the question is about the fall risk. When someone falls, that the fear can go for months, studies showing it. And they might be more stressed out when they walk around people and such. Say that person gets some therapy and they feel better, they are more stable. I've been working on IMUs on the feet and head to measure the variability of motion.
Okay.
And there is some therapy being applied so that variable changes. And I was thinking this with some, say, kinematics measurements might be a thing for fall risk if the person, the elderly, feels themselves more comfortable moving around and such, they will sweat less and maybe cortisol levels before and after some treatment or physiotherapy, let's say. Has anyone ever done something?
Exactly same application, no. But some applications are done with hydration monitoring, and some are done with children's pediatric applications where they generate sweat using hydrophorus, that I mentioned, where they apply small electrical current and generate the sweat. The same thing can be applied to elders as well. So very few, or in my understanding, one or two might have done, but not exactly the same application. But it's possible because we do have hydrophorosis technology where you can generate sweat in any individual, any health condition.
Yeah, great presentation. Thank you. You have shown a picture of the sensor on a horse.
Yeah.
Can you explain in general what is the performance of the sensor in animal code?
We did not do the analysis yet. We collected and still going on. This was because we collected the sweat and still analysis has to be done. We only collected for a few horses. We need to do more and do the results.
And I have another question from there. Are you planning to test other animals? Because I am asking you because maybe when we talk about the stress in animals, it's more straightforward, the measure of cortisol. Because as you mentioned, or maybe someone mentioned, the stress in humans is very variable. The source of the stress is physiological, emotional. But in animals, could be more simple to link it with the stress level. And sometimes we are handling our animals all the time, and we want to know the level of the stress because we are adding some bias there. So are you planning to test it in other animals?
We could, but right now we've not done it, but we can.
Yeah,
Yeah.
okay.
It's possible to do because there are two techniques as I mentioned. Kind of course we can apply to animals as well. It's possible to generate, and there are some works where they did for mouse as well. So it's possible to understand that part, but we have not done it, but it's possible to do it.
Do much sweat?
Of the endophorosis, or there's another thing called microneedles.
I mean, like, do they have sweat glands at all?
I don't know, we have to check, because I've seen some applications where they did on rabbits as well. There's some studies on the mouse, and mainly they use for interstitial fluid. Interstitial fluid, in order to understand the stress concentration, they use microneedles. It's kind of a needles, which is same minimally invasive, same principle as the continuous glucose monitoring. We have to see that it's possible or not. But if it's possible, our chip definitely works.
We have two last questions. So Jim and then last one there.
You said that the sweat channel for the chip is in combination with like hydrofluoric and hydrophobic components, but would it also channel oil? So just thinking like if there's a difference in cortisol measurements from like forehead and lower back, like the forehead which is made on sebum, so you're getting like a second secretion that is like contaminated, but would that be past that channel through that more specific channel?
So if I understood correctly, I did not listen, I did not hear properly.
Okay.
So this sweat from a forehead and armpit or different body locations is different. It might have oil in positions and all these things, right?
But the method of transferring the chip was using like hydrophobic components which would transport a water-based solution. Would that exclude an oil contamination from the forehead like sebum?
Yeah, we have.
Could that have like a different composition and might have a difference in location?
We have an inlet which has a fiber, which usually what happens is it absorbs others and only pumps the liquid, only the sweat samples. And usually the protocol what we follow is we ask them to not apply any cosmetics or anything before 1 day. And also we ask them to clean the face or whatever the body location we are interested in. And also wipe with alcohol wipes to make sure there's no contamination as much as possible. Still, if there's any contamination, minute level, that is not considered into it, but we have to see how we can take off that part as well.
Two questions. One is, do you know how big the magnitude of cortisol, like, dropping? Like, for example, noon versus 8 p.m. at night, you know the magnitude of it.
We did a literature survey where we did hundreds of papers on cortisol, and most of the cortisol was from 1 nanogram per ml to 125 nanogram per ml, and mostly was from 1 to 30 nanogram per ml. That's the range. And if it's a stress condition or if it's a disease condition, it could be higher. There are a few examples where you see 100, 200, and 1,000 as well. But average was from 0 to, and even specifically mentioning 0 to 15 nanogram per ml. That's a healthy variation.
So it can vary from 20 to 30 say, in a healthy.
Few examples, but with more than 100 analysis subjects analysis with different literature based analysis. And in that part, we found at least 90% of the people are from 1 to 15 nanogram per ml. More people. So there are few exceptional or maybe higher cases for sure, but more are in this range.
So now, I guess you need to cite more people to get a better sense of how they interpret this.
Yeah.
The other question is there a way to timestamp your samples?
Can you repeat it time?
Timestamp your samples. So like in a lot of like doubtful testing, where people say like we got heart rate at this time, this exact time versus later on. and we can take a snapshot of that, but is there a way to find out a timestamp for sweat collection? Because that can affect, the variation of sweat or concentration over the course of the day. Let's say you grab a sample maybe at 9 a.m. from a participant, but you process it 3 hours later.
Okay. It should not be. The reason is because that's why we're storing it in -80 degrees Celsius immediately. We should not, that's the reason we don't want to lose any molecules and read exactly the same time. As soon as the sensor fills with the sweat, take it, put it to the, we keep it back in the -80 degrees Celsius. There's another understanding is that if we collect at different time points and keep it outside, how much loss can happen? That's another question that can be done as well. Let's say if I take it and keep it 1 hour here, what is the percentage of loss? And if I do it immediately, what is it? If I keep it 6 hours, what is the loss? If I keep it for a whole day outside, what would be the loss? So this is another question that can be answered, but right now, as to avoid these losses, we immediately keep it in the -80 to preserve the molecules in the microbes.
Follow up to the first question. The concentrations that you talked about, are they in the sweat or in the blood?
In the sweat.
In the sweat. So what's the relationship between what you have in the sweat, what you have in the blood? So
Blood?
I assume at least it's the same, but to be in the blood, could it be higher in the blood?
Yes, you're right, because the cortisol is 95% cortisol is protein bound inside the blood samples. Only 5% is unbound. So we are detecting that 5%. So let's
So
say.
are you converting? Do you want to convert and say, oh, wow, this is very bad, in the blood it's gonna be so high, and so it's not?
No, that's what we need a validation for both to see what is the difference. Is it, let's say in this is one example here, I'll show it to you. Okay, yeah. So for example, here, the sweat, in sweat, it's 0.02 to 0.4 micromolar, whereas in blood, it's 0.1 to 0.8. So there's a difference because in blood, we have more unbound cortisols, but still 95% are bound to protein. Only 5% unbound proteins we are analyzing. And that too, when it diffuses and comes onto the skin surface, it's still less. The concentrations are definitely less. But we need that proper calibration curve to see this is the blood, this is the sweat, then we can, okay, now eliminate the blood, only depend on the sweat. This is because we have done the calibration data. But that part still needs to be done because we need a lot of statistical analysis to get that point.
Yeah, I think there's one last question online.
There's a question
We'll end with
online
that.
for you. Yeah, let me read this question. This is for future use of other hormones. How would you account for detection of hormones released at smaller concentration, such as testosterone?
Testosterone, estrogen.
Yeah, for hormone health issues,
Yes.
such as menopause.
Yes, yes. A lot of work on female health monitoring also going on to understand the estrogen levels, progesterone levels, and even these stress hormones, other stress hormones which I mentioned, epinephrine, serotonin. These are very smaller picomolar concentrations than the other higher level concentrations. That again depends on the sensing technology that we develop. If we can develop a higher sensitivity enough to sense the picomolar concentration of the samples, that's possible. And quite a few works are done on estrogen, progesterone. There's a new work on done which have a small ring the woman can wear on a ring, and they can understand their estrogen levels continuously. Not continuously, they have done it for one time, but it's possible to do using sweat samples.
All right, let's thank.